Hi there, what I've got for you today is a sample video about calorimetry problems. And calorimetry is just the exchange of heat between objects where we assume that no heat is lost to the environment. And it's not a bad assumption for a lot of what we do. A styrofoam cup is a really good insulator. So a styrofoam cup can be what we call a calorimeter, where it doesn't give off a lot of heat to the environment. So the problem we're going to be dealing with is, all right. This is something you would do in a basic calorimetry lab even. You take 80 grams of copper out of boiling water and put it immediately into a calorimeter, so insulated, of 450 milliliters of water at 19.6 degrees C. What is the final temp when the two adjust to their equilibrium temperature? So what is that final temperature? What do we have? All right. So we are going to have a bucket with some water in it, and we're going to take a hot bit of copper and dump it into the calorimeter with water. Exciting, right? So our two objects are the copper and the water. What do we have? 80 grams of copper, and it is coming out of boiling water, so its initial temperature is 100 degrees C. The final temperature, that's what we want, question mark. And if you look up the specific heat of copper in calories per gram degree C, you get 0.0923 cal per gram degree C. Okay, so water, we had 450 milliliters of water at 19.6 degrees C. We don't know the final temp, that's what we're looking for, and the specific heat of water is a nice 1. All right. Wow, we want to know what the final temperature is. Okay, so our equation that we're going to be using, Q equals mc delta T. So for each of these, I want to find out what the heat is that's lost or gained. So the copper is going to lose heat, it's going to cool down. The water is going to gain heat, it's going to warm up. So the Q for copper should be negative because it's losing heat. The Q for water should be positive because it's gaining heat. Now for both of these we need M, C, and delta T. We have M, we have an equation for delta T, and we have C. We don't have M, we have delta T and C. We need to know what the mass is of the water. And again, with water we're often going to be given a volume rather than a mass. The nice thing about water is, hey, it's really easy to convert. So 450 milliliters, well, that's 450 cubic centimeters. Cubic centimeters. At 1 gram per cubic centimeter, again, water, love it, we have 450 grams of water. All right. Then we want to find the temperature. Okay, so we have Q of copper, mc delta T. Mass is 80 grams. C is 0.0923 calories per gram degree C. And delta T, what is delta T? Delta means final minus initial, so I'm just going to say it's T final minus T initial, 100. Okay. The heat for the water, same thing. It's the mass, 450 times C, 1.0 times delta T, same thing. We don't know what T final is, I'm just going to put it in, and then T final minus T initial. All right. Now what do we do with these? Here's where we get to the idea of the conservation of energy, conservation of heat. Assuming no heat is lost to the surroundings, assuming this is a reasonably well insulated container, that means that this heat and this heat should be the same. The way we're going to write it is that, well, the sum of the heats has to equal 0. So in this case, the heat of the copper plus the heat of the water has to add up to 0. Add up all the heats, set them to 0, that means energy is conserved, no heat is lost, and we can figure out what T final is. All right, so we have an equation for the heat of copper, we have an equation for the heat of water. Now we're just going to put those two into this big equation. Okay, so let's put these together, I have the heat of copper, which is 80 times 0.0923 times T final minus 100. That is the heat of the copper, plus the heat of the water, which is 450 times 1 times T final minus 19.6 equals 0. Squeeze it in there. The only unknown is T final. At this point, it's just math, and it's not even that hard of math, because you just figure what this is, distribute it into both, figure what this is, distribute it into both, and you got it. Let me look at my numbers. I'm not doing that in my head. All right, we've got the first one. So 80 times 0.0923 times T final becomes 7.384 T final. And then that minus 738.4 plus, I can do that one in my head, 450 times 1 times T final. Yeah, I can do that in my head. Minus 450 times 1 times 19.6, 8820. Okay, I'm going to put the 0 over here. Let's combine the T finals together. 457.384 T final minus that, and that combined to 9558.4 equals 0. And then we can just bring this over to the other side, which means that. Okay, and divide both sides by this, and we get our T final, which is 20.9 degrees. All right. Now, as always, don't stop there. Stop and ask, is this a reasonable answer? I mean, did we answer the question? Yeah, we wanted to know the final equilibrium temperature. Is this reasonable? Well, okay, the answer needs to be between the two temperatures, between the 100-degree boiling water and the initial temperature of the water. So are we between 19.6 and 100? Definitely. And it's much closer to the water temperature, but we had 450 grams of water compared to 80, and it also, if you look at the difference in the specific heat, it takes a lot more heat to heat up water 1 degree than it takes to change the temperature, to drop the temperature of copper by 1 degree. So I would say this is totally reasonable. We've answered the question, it's a reasonable answer, and we've got the units there. Yeah, we're gonna be precise. I should probably add that, but I think that's good. So here's an example of a calorimetry problem. And if you have 3 objects, let's say you have, you take a copper sample and then you take a lead sample and put them both into a calorimeter of water, then it's just going to be the same thing, but you would add Q of the lead. So when you've got multiple objects, it's just add them all up, set them equal to 0. Figure out the heats for each, and you should be able to solve your problem. All right, good job.